This video is covering section 3.4, concavity, and the second derivative test. So we talked about increasing and decreasing, and that had to do with the first derivative. And now we're going to look at concavity, which has to do with the second derivative. So when we talk about concavity, a function can be concave up or concave down. So in this first example, you see that the function is completely concave up. Concave up like a cup, because it holds something. It's concave up like a cup. Then we have concave down over here in the second example, like a frown. So if I'm completely frowning, then we are concave down. All right. So when we talk about concavity, you need to understand kind of the concept behind it, not just pictorially. If you look at the function and think about its slopes, okay, so on this one, I have a slope of negative. Then here I have a slope of about 0, and then a slope of positive. So if I'm going from negative to 0 to positive, then the slopes are increasing. The function itself is not necessarily increasing, but the slopes are increasing. So the slopes are represented by f prime. So f prime is increasing. Therefore, if f prime is increasing, then its derivative, f double prime, is positive. Okay, so if we're concave up, then that means that the second derivative is positive. Same for concave down. If you look at the slopes from left to right, we have a positive slope, here we have a 0 slope, and here we have a negative slope. So that means that the slopes are decreasing. Again, that does not mean the function is decreasing. It means the slopes are decreasing. Therefore, f prime is decreasing. Therefore, the second derivative is negative. Okay? So if we want to test for concavity, it's really the same thing as a test for increasing and decreasing. Before, to find increasing, decreasing, we found f prime and then found the critical numbers and did a sign chart. We're going to do the exact same thing for concavity, but we're looking at f double prime. So the test for concavity, you want to find f double prime. If f double prime is positive on an interval, then that means that f is concave up on that interval. And if f double prime is negative, then that means that f is concave down. All right, so when we talked about f prime, when I changed from increasing to decreasing on f prime, or for f, and f prime changed signs, we had a minimum or a maximum occur there. So when we have f double prime changing from positive to negative, what we have is called a point of inflection, or we could notate that as, or shorten that as POI. So a point of inflection of the graph of f is a point on the graph at which the concavity of the graph changes. That is, f double prime, or the sign of f double prime changes. Okay, so that's important. So now we're going to be looking at points of inflection, just like we were looking for mins and maxes before with f prime. So given that f double prime here, find the x values at which f has a point of inflection. Now, what's really nice is they've already given us f double prime, and they've already factored it for us. So all we have to find out is when this is equal to 0. Also undefined, but this function is just a polynomial, so it's not undefined. So if you look at these factors, this f double prime would equal 0 when x is 3 and negative 7. And again, you set it equal to 0 or undefined because that's where we have the possibility of a sign change. So then we're going to create a sign chart for f double prime. And I like to label my sign chart so I know exactly what I'm looking at. So at negative 7 and then at 3. So if you go and test some values, if you go to negative 8, then that's a negative. Squared is always going to be a positive, and then negative 8 plus 7 is a negative. So negative times a negative is a positive. At 0, we'll have a negative, and at 4, we'll have a positive. So what you can tell about f from that is that if f double prime is positive, then f is concave up, like a cup. If f double prime is negative, then f is concave down like a frown, and then we're concave up again. Oh, you know what? I made a mistake. Just kidding. When I plug in 4, that is not positive. Just kidding. If I plug in 4, this is actually going to be a negative. My bad. Okay, so this is going to be concave down. So that's, again, why you should never assume that it goes positive, negative, positive, because we could have a sign change here. And I want to mention why it doesn't change sign, and that's because of this squared right here. When you have a squared, that is going to typically not change sign. So what this would look like typically, so from negative infinity to negative 7, I'm concave up. And then at negative 7, I'm changing sign. So what I have is a point of inflection. So right about here at negative 7, I'm going to start changing to concave down. So you can see how that point of inflection works. At negative 3, what could happen is, since that picked up as a critical number, what could happen is that might bottom out like this. And actually, that might be a little extreme. Let's see, let's try this. So what happens is that might have a slope of, let's say, 0 here. So it bottoms out, but then it's going to continue going concave down. Much like, this is not a very good graph, but much like a cubic function would. So it's decreasing, and then it continues to decrease. All right, so F, so here's how we would write our final answer. F has a point of inflection at x equals negative 7 because F double prime changes sign. Now, you do not have to specify it's changing from positive to negative. You just have to say that it's changing sign. Okay, for example 2, I'm actually going to change the function. This is too complicated of a function that I want to go into right now. So I'm going to switch this to a much easier function. So we're going to call g of x, x to the 4th power minus 4x cubed. So change that for me. Okay, so we want to find all the intervals on which the graph is concave up or down and find all the points of inflection. So we need to find the second derivative, but before that we have to find the first derivative. So g prime will equal 4x cubed minus 12x squared. Now, I don't have to do anything. They did not ask me anything about increasing or decreasing, so I'm going to go straight to g double prime. So that would be 12x squared minus 24x. So now with this function, we want to find all the critical numbers for g prime, so where this is undefined or equal to 0. This is a polynomial. It's never going to be undefined, so we're going to set this equal to 0 and factor. Okay, so after we factor, we get the x values to be 0 and 2. So now create a sign chart for that. So for g double prime, if we plug in a negative 1, and I like to go into the factored form, that's a negative times a negative is a positive. Positive 1 is a positive times a negative is a negative. 3 is a positive times a positive, which is a positive. Okay, so we know that g is going to be concave up on the intervals from negative infinity to 0, unioned with 2 to infinity, and make sure you list your reason why. Why do we know it's concave up? Because g prime is greater than 0. Then g is concave down on the interval from 0 to 2 because g double prime is less than 0. Okay, so that's the statement that I'm looking for, and that's about as shorthand as it gets. So now I also want to find the points of inflection. So g has points of inflection at x equals 0 and 2 because g double prime changes sign. And actually for this one, I want to mention, if you go back and look at the first example that we did, the question said to find the x values at which the f has a point of inflection. So we said it has a point of inflection x equals negative 7. Most of the time, you will just be asked to find where it is at, the x values. But if you look at the language on this one, it says find all points of inflection. So actually what I did down here is I actually showed where they are at, what x values they're at. So we actually want to make this a little bit better by stating what the actual point of inflection is. So all you have to do is plug in 0 and 2 into the original equation, and then you'll get your points of inflection. So let's go back and let me change this by plugging in 0 and 2 into my original equation. Okay, so my original equation was x to the 4th minus 4x cubed. So if we plug in 0, then we get the point 0, 0. And if we plug in 2, we'll get negative 16. So g has a point of inflection at 0, 0, and 2, negative 16, because g prime changes sign. So just make sure you look at how the question is phrased so you know how to do the problem. Okay, so we just looked at the second derivative test, and the second derivative, not the second derivative test, sorry, the second derivative, and that will tell us where the function changes concavity. But now we have what's called the second derivative test. Now, the first derivative test that we learned in the last video was a test for relative extrema. That means where we have a min and max. The second derivative test is actually testing for the same thing. The second derivative test is not testing for where I have a point of inflection. It's testing for where I have relative extrema, so mins and maxes. Okay, so it's two different tests that are testing for the same thing. And you need to know when to use each one because you're going to have to know in different scenarios. Sometimes you'll have to use first, sometimes you'll have to use second. So if my first derivative is 0, so if my first derivative is 0, what that means is I have a horizontal tangent. Okay, and then if f double prime is greater than 0, that means that we are concave up. So if you're concave up and have a horizontal tangent, then that means the only point you could be is right here. And so right there is going to be a relative minimum. Okay, so if you know that both f prime is equal to 0 and f double prime is greater than 0, that means concave up, then that point, f of c, is a relative minimum. Okay, so you can say the same thing if f prime is equal to 0, horizontal tangent, and if f double prime is less than 0, that means we're concave down. So when we're concave down and f prime is equal to 0, that horizontal tangent occurs at a relative maximum. So you can see we're using the second derivative to tell something about the mins or maxes. And then if f prime is 0 and f double prime is 0, that's actually inconclusive. It could be a relative min or max, but we can't tell because there's no change in concavity there. So it's inconclusive, and if we're inconclusive, then either that means we're going to have to stop there, or if we can, we're going to use the first derivative test. Okay, so let's look at example 3 and use the second derivative test. So using this function, we want to find all the relative extrema, so where I have mins and maxes. So we're going to first find f prime, and that's going to be 1 minus 2 cosine. And again, part of the second derivative test, we want to know when f prime is equal to 0. So we're going to set this equal to 0 and get cosine x equals, that'll be positive 1/2. And on the interval from 0 to 2 pi, that's going to be pi over 6 and 5 pi over 6. Okay, now, obviously, you could use the first derivative test. If I was to use the first derivative test, I would make a sign chart. Uh-oh, what's going on? Uh-oh, hold on. Okay, sorry, I accidentally clicked something and it was bringing up a new page. So if you were to use the first derivative test, you could do that. You'd make a sign chart right now with pi over 6, 5, pi over 6. So why am I asking you to do the second derivative test? Well, if it did not specify, then I would use first derivative test here. It makes more sense. But sometimes you'll either be asked to specifically use the second derivative test to make sure you know it, or in the next example, example 4, you have to use the second derivative test, and I'll show you why you would have to when we get to example 4. Okay, so using the second derivative test, we know when f prime is equal to 0. So now we just need to find f double prime. So the second derivative is going to be -2 sine. Oh, what did I do wrong? I did something wrong. I'm sorry, guys. Okay, hold on. This is supposed to be a sine. I'm reading my notes wrong. I apologize. Let me go back and change this really quickly. It's a bummer on these videos because I can't go back and edit, so all my mistakes you get to see. All right, so then this should be true because cosine x equals 1/2 wasn't even pi over 6. It's sine of x equals 1/2 is pi over 6 and 5 pi over 6. I apologize, guys. So let's continue on. So f prime is going to be -2 cosine. I'm trying to go too fast and making mistakes. All right, so now we have f double prime. I don't have to set this equal to 0 because I'm not looking for concavity here. I'm looking at these values, pi over 6 and 5 pi over 6, and testing to see what they are. So f double prime at pi over 6 is -2 times cosine of pi over 6, which is -2 times root 3 over 2. And so all we're concerned about is what is the concavity at that point. That is negative concavity. So what that means is if I have negative concavity and a horizontal tangent, and it helps to draw the picture because sometimes people get this confused. So negative concavity, concave down, with a horizontal tangent is right here. So that means at pi over 6, we have a maximum by the second derivative test. Okay? So now let's try the other point, 5 pi over 6. So at 5 pi over 6, we have -2 cosine of 5 pi over 6. And that's actually going to be -2 times -root 3 over 2, which is going to be positive. So therefore, I have a concave up graph and at a horizontal tangent line. So therefore, we have a minimum. Okay, so let's go ahead and write our final statement here. So we want to say that f at pi over 6 is a relative max. And you can't just say because f double prime is concave down, because you have to be both concave down and have that horizontal tangent line. So I need to state two things here. It's a relative maximum because f prime at pi over 6 is equal to 0, and f double prime, not triple, at pi over 6 is less than 0. Okay, and then for f at 5 pi over 6, that's a relative minimum because f prime at 5 pi over 6 equals 0, and f double prime at 5 pi over 6 is greater than 0. Okay, so make sure, again, you have this final statement. All right, for our last example, like I said on example 3, you didn't have to use a second derivative test. I just told you to. But for example 4, you're going to have to use a second derivative test, and let's see why. So it says let g be the function whose derivative is given by this. So we're given the derivative this time, and you can see that it's an implicit derivative. So what I can't do is figure out what the original equation is. And I also can't really do a sign chart here because I have both an x and a y. So this isn't really going to help me to use the first derivative test. So we're going to have to use the second derivative test. So they give me a point at g2 equals 3. Determine if g of 2 is a relative max, min, or neither. So what we need to find out is, first of all, we want to make sure that at this point 2, 3, the derivative is 0. Because if it wasn't 0, then it's not going to be either a max or min. So how we notate this, and we're going to use the notation dy dx, and I like to use that more specifically because we're both in terms of x and y. Now, this big long vertical line means such that. So this is dy dx such that we're at the 0.23. So down here at the bottom, we're going to put 0.23. So then we're going to plug in 2 for x and 3 for y. And just make sure and double check that it's equal to 0. So 3 times 2 minus 2 times 3, yes, that will equal 0. Okay? So that's going to apply, but now we need to see what the second derivative is. So to find the second derivative, we're going to have to use implicit differentiation. So derivative of 3x with respect to x is 3 minus 2 dy dx. Now, if I want to find out what the second derivative is at the point 2, 3, then all we have to do is plug in the derivative at the point 2, 3. And what did we find it to be? 0. So we can just plug in 0 here. We get a positive 3. Positive 3 is greater than 0. Therefore, since dy dx is equal to 0, and the second derivative is greater than 0, g of 2 is going to be a relative minimum. And again, it helps to draw a picture. So if I know that it's concave up like this, then I have a relative minimum. Okay?